And this is what I will do. I will show you my design. Assume that A is 0, 0, 0, 0, 0, 0, 0, 0, 1, and B is 0, 0, 0, 0, 0, 2. So assume that this is my case, then I will create C like this one. Oh, because it has size 3 and size 2, so I will create size 5, and then I will multiply these things like this. I write the result of these things into these two. And I will write the result of these things into these two. And I will write the result of these things into these two. After this, I will check whether these kind of places have carryover or not. So I will handle carryover. Afterwards, I will check, I will insert the result of these two to these two places. I will insert the result of these two into these two places. I misquoted it. And then I will write the result of these two into these two places. And afterwards I will do carryover. Then it will fill. So this is my design. And if you have any questions about my design, ask me. So after this, what I will get will be this. Right? This is the result that I will get after this. Of course, these numbers may be other numbers. These numbers may be non-zero numbers, but doesn't matter. This will at least hold the result. So let's do it. First of all, to do it, the important part is this portion. We should break up the result of this 3-digit multiplied by 3-digit. It could be maximum 6 digits, right? So I will break this up into two parts. So top part and bottom part should be found once two numbers are multiplied. So what I will make is are two functions, top 3 function, bottom 3 function, right? Top 3 and bottom 3. And top 3 can be found by number divided by 1,000. And then this symbol represents either floor function or some program language has integer, and it cuts the fraction part or other things, replacing this, then it will return top 3 numbers. Sometimes it could be 0. And then bottom 3 number is nothing but this number n minus 1,000 times this top portion removed. So top and bottom can be always decomposed. Any questions? In other words, if you multiply 900 by 800, then the result is this one. Then top 3 is this one, bottom 3 is this one. This function does this thing. And with this one, we are almost ready to program it, so I will show you. With this function, with ABC, as I mentioned before, with ABC input, output, as I mentioned before, we do this thing. For I running from 1 to size of A, and then for J running from 1 to size of B, and then X is the result of AI and then BJ. Any questions? I multiply two numbers, right? Here, one number here, one number down, one number up, one number down. Then now, I should store top 3 in the position C I plus J minus 1 position, top 3 of this thing, and bottom 3 portion at C I plus J position. So this is what I do. So each time, so for instance, if I multiply 1, 200, 300, and then 25, 900, 100, then what I do is this one. This is A, and this is B, this is C. Then I store this result in these two boxes, right? These two boxes. Top number of this result is stored here, like 2 is stored here, and then 5, 0, 0 is stored. This is what I did. Any questions? And then ij handles the position, right? ij handles this position. As I moves, this box moves, right? So this handles everything, and I end this for loop, right? Then essentially, we fill every boxes, and then the only thing remaining is doing carryover. We should carry over. Before doing it, you can do carryover, but for efficiency, I will just finish it and then carry over simultaneously. So it doesn't matter to carry over right at individual step or at the same in the end. Then for k running from size of c, right size of c to 1 by decreasing order, right? By -1, we use this. If ck is greater than or equal to 1,000, then it means it has a carryover, right? Then that carryover top portion should be moved. That means the previous digit should have, I didn't write this thing. I should have mentioned, yeah. Previous result plus 1. Previous result plus this result, right? This result is added to the previous result. I forgot this thing. And here, we should write this way. This previous digit should be added by the top portion, top 3 portion of ck. Do you follow me? And after this, bottom 3 portion is completely specified. Then we are done, right? Then we are done. So we can, this is equal, this is not plus equal, because we already moved this top portion is equal, and then, and if, and then, and 4. Then this completely adds the thing. Please check whether, of course, if you don't want to add too many numbers at the same time, then you can move this end, this loop portion, to the bottom so that you can do these things each time, but it is inefficient.
If you wait till the end, there was a chance of adding 4 digits.
That's right. That's the reason I said if you don't like it, then you can move this loop to the bottom. Then each time it will do the carryover and then go up and then do the second multiplication and then do the carryover and so on. So this is just for the explanation. I said it's okay to write it here, but if you don't want to, if you don't want to add too many numbers, then you can move this down. This is the only difference. So please browse this thing and check whether it will run or not. So it will completely run, right? So roughly these are the necessary steps, right? So what I wanted to see is this one, whether you have ability to track down these kind of indices in the complicated formula that you will see in the course. In the future, you will create finite element to solve PDE problems. Then individual stuff should be handled like this. I asked a small size problem before. Someone just hardwire everything instead of writing indices like this. So I don't want to see that kind of thing. So the key part is using indices. This way you can just completely handle all the multiplication in between, and then afterwards you can handle. So I completely mentioned this thing, and then if you don't want to add 2 big numbers, then you can move this portion down to this portion. In other words, each time you multiply one number and the top row, and then you can do carryover. And then you multiply second number and the top number, and then do carryover and so on. So just a position problem. But for efficiency, I moved this up. Any questions? And the second one is this decimal number to binary number. And decimal number to binary number can be done this way. So assume that input is stored here, n is input, then this is all you need to do is this one. While n is positive, you can do the following thing. If n is odd, then you create an array, and then I will say position is 0, A is an array, and then position A position is equal to, because it's at 1. Otherwise, A position is 0. In other words, if it is even, it's 0. And then if it's done, right? So this is a portion. And afterwards, we can write it this way. We can replace n by n over 2. This means either floor function or integer part that can handle n. Then we increase the position. This means position plus 1. Then essentially done. So by doing it, you create A0, right? So take a look. When you want a binary number, we need A0, A1, A2, A3, and so on, right? Right? You need these stuffs, right? So A0 is determined by this, A1 is determined by this, A2 is, so you get all the numbers. If you want to rearrange it, you can reverse it by writing the AN first, right? Going down is possible. So it's done. Any questions?
Sorry, so what was the n divided by 2?
N divided by 2 with floor function or integer function. So I will show you an example. Pick any number. Not a big number is good. So pick any number, then I will show you. 25 then. This is the situation. 25, right? 25 is odd, right? So A0 is 1. Do you follow me? And then divide by 2, then it is 12.25, but integer removes this portion, is 12. It's odd, so A1 is even, so A1 is 0. And divide this by 2, then divide this by 2, then 6, right? And then because of this, 0. And divide this by 2 and 3, and this becomes 1 because it's odd. And then divide this by 2, then 1.5. So A4 equals done. This is it. So straightforward method. The next one is these two unsigned integer, and presume that these are given in this pattern, like A represent bit representation, right? Then this is the idea. Assume that this size is given, right? Length of this array A is size, called size. Then for I from 1 to size, we do this thing. Initially we say sum is equal to 0. Sum is equal to 0, and sum is equal to 2 times sum plus these kinds of things, AI, right? AI. And then return the sum, right? Then done. So when you want to convert this, then you write this thing. Then when you go to this thing, this means 2 times this one, right? So 2 times this is done, and then if you go to, and 2 times this result times this, and so on. So you go these things all the way down, and then return the sum. Do you want to see it? For instance, pick an example, such as this one. 1, 1, 1, 0, 1. Then this is what? Sum is initially 0, right? And then you use this one, then sum is equal to 0 times 2 plus this 1, right? And then it is 1. Now, sum is equal to sum plus, right? This sum plus sum times 2 plus this number. Then 3, right? And then sum is equal to this number times 2 plus 1. And then sum is equal to 7 times 2 plus this number, 14. Sum is equal to this 14 times 2 plus this number, then it's 29. So it's done. So please browse these things and ask questions. Finally, assign the integer to bits. Of course, this isn't the only way. I'm just giving you one example. So assigned to bits, n is this one. N is input, right? Input is n. And output will be bits, right? Bits. Output will be bits, 0 or 1 combination bits. So this will be our output. So let's do it. So initially, this is what you do. Assume that we are using 32-bit integer, but 64-bit isn't very different from this one. Then for I running from 32 to 1 by decreasing, right? By decreasing 1. Then if n is odd, by input is odd, then the least significant digit, right? This 32, right? This digit is 1. Otherwise, this digit is 0. Any questions? And we do similar thing. We replace n by n over 2 with integer function or floor function. Then n is now reduced, right? N is half or a little bit lower. Then we add this condition. If n is equal to 0, then break. To do this thing, it's good to use this thing. Initially, we fill A with 0, right? We fill A with 0. This way, if we break, we have zeros, right? Initially, we have zeros, and then we fill A32 with 1 or 0 and so on. But if somehow this number becomes 0, then we don't have to go any further. And then we do these things, right? So essentially, this converts the number to bits. Now, the next thing is inversion and adding 1. Right? Inversion and adding 1. But if you have a question about these things, ask me. Then the next thing is this one. For I equal to 1 to 32 or 64, it doesn't matter, right? If AI is equal to 1, then BI is equal to 0. Otherwise, BI is equal to 1. So we are creating BI array, B array, right? From A array. A array had bits. Now B array will have the result. Now we invert the stuffs. And final thing is adding 1. Final thing is adding 1 for I from 32 to 1 by decreasing, right, by -1. If AI is equal to 0 in the least significant digit, then we increase 1. Adding 1 is done, right? And then we break. In other words, we don't have to run this loop, this for loop completely, right? We don't have to run this loop completely, right, if this happens. But if this does not happen, then what should we do? Because we have this thing, we need to add 1 to the number that, because it's else case, right? If else case, it means AI is already 1, right? Because we are adding 1, then AI becomes what? 0. AI becomes 0. So at each point from the least significant digit, we check whether it's 0 or 1. If it is 0, we add 1 and stop, right? We add 1 and then stop. We break and then return the result. Oh, sorry, it's B. I was confused. This is B, sorry. I mean B. Sorry for the mistake. It should be B, right? Because we already inverted. A is the bit representation. B is the inversion. Now, I want to add 1 to B. So if B is already 0, least significant digit is 0, we just add 1 there, and then stop, right? Add 1 and then stop and then end the program. But if it is already occupied by 1, then we will have carryover. Because we are adding 1 to 1, the result should be 0. And then it goes to the next round, right? So 31 bit should be checked. 31st bit should be checked. And if it is 0, then we add 1 and then stop. But if it is not 0, then we continue all the way up. So this is it. So I completely gave you pseudocode of the 4 cases. And if you have a question, ask me. If you don't, then I will answer other questions, other problems. The next case is this one. The most important thing in number representation is the first line that I mentioned, right? First line said this. We usually have a point here, and then A0, A1, A2 digits here, right? And then A minus 1, A minus 2 digits here, right? And then, for instance, if you have these kind of numbers, the meaning is this. A0 times base to the power of 0, right? And then A1 times base to the power of 1, and so on, right? And then here, A negative 1 times base to the power of negative 1, and so on, right? So this is the definition. And from this, everything follows. So we have 12.5 to the 5 with base 10. Because of this, it means 2, 1, and 2, and 5. These 3 digits are used. Then 1 means 10 to the power of 1 plus 10 to the power of 0 plus 10 to the power of negative 1, right? So if we rewrite it, it means 10 plus 2 plus 5 tenths, or 12 plus 1/2, or, yeah, this is it, right? 12 and 1/2. Then I want to write it using base 8. Then it is 8 times 8 to the power of 1 times 1 plus 8 to the power of 0 times what? To make 12, 4, right? And then 8 to the power of negative 1 times 4, right? 4/8 is 2 1/2. Because of this reason, we can write it this way. 4.4 with base 8. So most important thing is this definition, right? This definition is the most important thing. Any questions? The next one is invert and add 1 scheme. We have negative 12, right? With 8 bits, right? Then negative 12 equals negative, and then I will just convert this to bits. Then 12 is 0, 0, 1, 1, 0. This is the 12, right? Because if you don't understand these things, you can do this. It's a 0 times 2 to the power of 0, 0 times 2 to the power of 1, and then 1 times 2 to the power of 2, and then 1 times 2 to the power of 3. Then it is 1 times 8 plus 1 times 4, then it is 12. Any questions? Then, now, we want to do minus, so we invert these things, right? Invert these things, and then add 1, right? Then, eventually what we will get is this one. Adding 1 means carry over to this position, so this is the result. The next case is negative 5 I will write the problem first. The next case is the IEEE type real number interpretation. So this is given, then what does this number mean? So first of all, this 1 means sign, right? Sign is negative. And then 1, 0, 1, 1, 0 means exponent, right? Exponent form is this one. Bias is 1, 0, 0, 0 minus 1. So if we add, then 1, 1, 0 plus 1, then it is 7, right? 7 is the exponent. Do you follow me or not? And then fraction is 1, 1, 0, 0 is the fraction, and then fraction means, normalized fraction means 1.1100 in binary representation. So this means 1 plus 1/2 plus, I will write the power notation so that you can consistently read the note later. So this is it, right? This is the representation of the fraction part. So it is 1 plus 1/2 plus 1/4, then 7/4. So if we multiply these things, then minus 2 to the power of 7 times 7/4, or minus 32 times 7, then it is minus 224. So this number represents minus 224. The next case is minus 5.5 with base 10 can be written in the same pattern, right? Before doing it, I will convert it to bits, right? Bits. Just a straightforward bits or binary numbers. Then it is, I will write it this way. 2 to the power of maximum power possibly is 2, right? And then 2 to the power of 1, 2 to the power of 0, 2 to the power of negative 1, and so on, right? So how many? 1. And then 0, and then 1, and then 1. Right? So it's exactly identical, right? These are identical. Then because of this, we can write this number this way with binary representation. So I want to write the number in the standard form. Right? Then exponent is determined and normalized portion is determined, right? Exponent portion and normalized portion should be written because bias is 0, 1, 1, 1, 1, This is the zeroth power. This is the first power usually. And then second power is this one, right? This is the second. Do you follow me? This is the bias, and usually this is the first power, and this is the second power. So we know the pattern. Sign is plus, right? Oh, minus. I didn't write it. This is separate, right? So sign is minus. So we should have bit representation like this. 1, right? 1. And then exponent representation is given here. Power 2 is represented by this number. So 1, 0, 0, 0, 1. And then fraction part should be represented 0, 1, 0. And then we have one empty space, right? So this is it. Any questions? And finally, if you can read these kind of numbers, then you can find the maximum or minimum. Assume that you are designing numbers, then you need to know what kind of maximum or minimum is required in your coding. So let's consider the exponent part. This is a sign bit. Sign bit is not important. Exponent bit and fraction bit. So this is 10. There are 10 bits, and then there are 21 bits. Then maximum possible pattern is 1, 1 all the way up to this one, and 0. If everything is 1, either not a number or infinity. So if we exclude not a number and infinity, this is the possible maximum power. And fraction part can have maximum representation by having every year 1, right? Every year 1, right? So this is the maximum number that we can represent. Similarly, minimal number we can represent is everything is 0. And then everything is 0 except the final number, right? Except the final number. Because if everything is really 0, then we have 0. And other than 0, what is the smallest? So if any number that you want to represent is above this and below this, then it's above this, then it's called overflow. If your number is below this, between 0 and this one, then it is underflow. Now it's time to just interpret these things. So let's interpret the first one. Then, usually, this number plus 2, this number plus 2 is nothing but 2 to the power of 10. Right? Because if you add 1, then everything is filled. If you add 1 more, then it will overflow to 2 to the power of 10. So because of this reason, this number is 2 to the power of 10 minus 2. But because of bias, we have this as exponent, right? Bit reading gives us this number, right? This is the bit conversion. But this number minus bias gives us exponent. And bias is, by definition, 2 to the power of 9, right? M minus 1. 10 minus 1 minus 1, right? So this is a bias. So total is 2 to the power of 9 minus 1. Then 2 to the power of 9 is 512. So 511. So this is the exponent. This is the possible maximal exponent. And this portion can be also analyzed. 1 point, this one is from normalized portion. And there are 21 digits that you can use, right? 21 digits of ones in binary representation. Then I will write it upstairs. It means 1 plus 1/2 plus 1 squared up to 2 to the power of 21, right? Because there are 21 digits. Then, if we add 1 over 1 to the power of 1 over 2 to the power of 21, then it will become 2. So the end result is 2 minus this one, right? If we add this number on the right hand side, it will carry over all the way to the left, and it will become 2. So this is it. So now we combine these things together. So maximum number that we can represent is this number multiplied by the power 2 to the power of 511. Did I say 11 or 10? 511, right? So if we write it, then it is 500 2 to the power of 520. And then 2 to the power of 400 something, right? So this is the maximum number that we can represent. It's extremely large. Yes?
Why are you raising 2 to the power of 511? I thought the exponent was some number minus the bias.
So exponent should be some number minus bias, right? So some number is this one. 1, 1, all the way up to this one and 0. This is the number minus bias, right?
Right.
Then, in binary representation, then this number is what? 2 to the power of 10 minus 2. Because if you add 2, then it will become 1, 0, 0, 0, 0.
Right. And then
Minus bias. What is bias?
minus 511. Right.
Do you follow me?
That is 511.
Yes, that is 511. So this is the maximum number that we can represent. And the minimum number we can represent can be analyzed. Minimum number has fixed exponent, right? Fixed exponent is 1 minus bias is the fixed exponent, right? When all the exponents have zeros, then we have 1 minus bias, then 1 minus 511, then minus 510 is the power. And the smallest number that we can represent is 0.00 all the way up to this. So there are 20 zeros, and then final one is 1. If even this one is 0, then it represents 0. So the last one cannot be 0. So this is the smallest number that we can represent. Then, by definition, this means 0 times 2 to the power of negative 1, 0 times 2 to the power of negative 2, and all the way up to this one, 0 times 2 to the power of negative 20, and then now 1 times 2 to the power of negative 21. So after this, what you get is 2 to the power of negative 21. If we multiply these two, then minimum number is 2 to the power of negative 21 multiplied by 2 to the power of smallest power. So we get 2 to the power of negative 531. This is it. So we can represent all the numbers from this to that, and then we sometimes decide what to choose by either rounding off or truncation. So this is the summary, and at the same time I completely solved the problems. And now, if you don't have a question, I will begin to cover the next chapter, covering numerical techniques. But before covering numerical techniques, I will let you know the goal of this course. Of course, all of these are necessary, but the major thing is this one. We want to solve differential equations over some domain, right? Then, what do you do? Eventually, there are many techniques, but the most important thing that we will cover is finite element method. So we discretize the given domain using appropriate triangles, right? Using appropriate triangles. And at each triangle, we find appropriate base functions, and then using basis functions, we can approximate the function, and then we solve the differential equation. Theoretically, it's not very difficult, but practically, you should program these things, right? So you completely discretize all details here, right? All the details using triangles. And then you solve the differential equations using these basis functions. So this is the goal. So to do these things, we need strong computational technique, meaning coding skill, and then nice idea about numerical approaches. Any questions about this? So this finite element method, why do we study these things? Because we want to solve PD problem. When I made a problem, I somehow omit this thing, but I will later replace the file by correcting this thing. So we want to solve this kind of problems. Plus an equation, then if we solve the equation and then we have boundary conditions, then we can consider the result surface, right? So we want to solve a differential equation satisfying the boundary condition by doing what? Program. By programming, we want to solve this. So later, I will let you know about the way you discretize and then to calculate appropriate basis functions. So roughly, this is the idea. At each position, we define basis function like this, right? So we define basis function like phi1 up to, say, phi200. So we define phi1 up to phi200 covering the whole domain. Then finite element method is this. Using these things, we find the best approximation solving this equation. Best approximation solving this equation. Then, once we solve the equation, we will find the appropriate coefficients. So Ci meaning C1, C2 up to C200, right? Then the answer is this. Our answer is C1 C1 phi1 plus C2 phi2 C200 phi200 is the answer. So we will learn about the theory very easily, but the problem is this. Once I learn, I let you know these things, you should program these things to solve problems. So you should handle indices and the basis functions, and I don't require you to really automatically discretize the domain. In fact, in some courses in computer science, people try to discretize a given domain automatically using triangles. Or if it is three-dimensional case, by tetrahedron they can discretize the given domain. Two-dimensional or three-dimensional domain can be discretized, but we don't cover that area. We assume that it's already discretized. Then, under this assumption, how to solve this kind of things is our major concern. Then, as I mentioned, we begin with numerical techniques, and I somehow found that almost all of you know about numerical techniques, but because there are some people who didn't take the course, I will mention this thing anyway. First thing is solving a problem, meaning finding the solution. So this is the zero line. Then we want to find the solution. How can you find the solution? There are some typical ways, and one way is this one. Bisection. We capture the domain having the solution, right? So we find the left side and the right hand side capturing the solution. And then we find the smaller interval than the given interval by halving the interval, right? So we halve the interval, and then we capture the solution inside the smaller interval. And then we halve the interval and then half the interval, and so on. So we eventually capture the solution, and this method is called bisection method. And roughly programming, this isn't difficult. We initially say left point and right point, and the left point and right point should have different heights. Left point could have positive height, then right point should have negative height, and vice versa. Then we find the middle point, right? So from this, we determine middle point by doing this averaging, right? So by averaging, we find the middle point. And then this middle point may have the same sign as left or right, right? May have the same sign, or sometimes it could be exactly the solution, right? Sometimes it could be the solution or left or right. So if it is left, then the solution exists between middle and right. If it has the same sign as right, or let's say if it has opposite sign, right? If M has opposite side as the left point, then the solution should be between L and M, right? If it is plus and this is minus, like this, right? If this happens, then middle point and left point should contain the solution, and we can shrink this one more time by using middle. So always finding middle and then tracking down the solution. So this is called the bisection method. So we can loop these things, right? So initially left, right is given, and then we derive middle point, right? And middle point become either left or right, and then we run these things, and then we shrink and shrink, shrink, and then eventually we say solution is between these 2 points, and then we find the solution. Any questions? The next case is Newton's method, very famous method. Newton's method comes from the equation, derivative definition. Derivative is equal to limit as h goes to 0, y of x plus h minus y of x. So this is the definition of the derivative at x. And we aim this thing. We want to have zero result, right? This is our goal, right? We want to have zero result. In other words, after doing our approximation, I want to have zero result. So we say this is equal to 0. Then from this one, we can find the relation between the two. So let's say, because h is not very nice, I will rewrite h. h is equal to, let's say, x n plus 1 minus x n. So we have two different points, and then I will use these things. And I will replace x by xn, and then x plus h by this number. Then what happens is y primed of xn equals limit xn goes to xn plus 1 goes to xn or vice versa, right? So do you completely follow me? So the same definition with xn plus 1 and xn, and then the goal is having 0 here. So our goal is having better xn, creating 0 value. Then if we solve this, if we drop the limit, then it becomes approximation, right? If we drop the limit and write it this way, and then we can take reciprocal of both sides. The reciprocal of the left-hand side is 1 over y primed of xn. The reciprocal of the right-hand side is y of xn, xn plus 1 minus xn. Then we multiply both sides by y of xn. So we multiply both sides by y of xn. So I multiplied this side by y of xn, and then equals this one. I will write equals on the right-hand side. Then eventually we will get this. So this is Newton's method. By using this method, we can find the solution, and I will show you how you can use this thing. Initially, you pick some nice point close to the solution. Even though it's not very close, it's okay. And then from this, you apply this thing. x0 is given, x0 is given, x0 is given, function y is given. Function y is given, function y prime is given. So all these can be calculated. Any questions? All of these things can be calculated, right? x0, 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 y of x0, y prime of it. All of these things are calculated. Then from this, we get x1. And then now this x1 goes in, and all these can be calculated, and we can calculate x2. So we eventually calculate all the numbers. So from x0 we calculate x1, from x1 we calculate x2, and so on, and then xn. And somewhere you may see that two results are very, very close, or sometimes even the same. Then we stop. So this is Newton's method. And before going any further, I will show you the web page having these things. So I explained these two things, right? Bisection method using opposite sign interval, right? We have an interval giving opposite sign at endpoints. So you keep these things to track down the solution. And this is the Newton's method that I described. Now the next method is iteration method. Generally, it can be found differently. I found the iteration. Iteration is this. As you can see, from x0, we found x1. Right? From x1, we found x2, and so, right? So we can find these things from the previous result. And generally, we can say this. From xn, we may be able to find xn plus 1. So by doing something, right? By doing something. So let's say this. By doing f, we may be able to find this thing. So this kind of scheme is called generally iteration method. Right? By doing this thing, we can find the next one. And then by doing this thing, we can find the next one, and so on. So generally, iteration method can be considered. And Newton's method is one of them, right? Newton's method is one of them. In this case, f function is what? These things, right? These things is f function. The whole thing is f function. Then the next thing is Newton's divide difference defined by just this, and the usage of this is important because we can replace the derivatives using just fraction of differences, right? Fraction of differences. By using fraction of differences, we can replace the derivative. So this is the major goal, and we can define these things repeatedly, right? Initially, we defined one function value minus another function value over some difference, but now we can define these kinds of things recursively. And there are some properties that I don't want to mention. You can read these things if it's necessary. And using these things, we can derive an important method called Mueller's method. And in the course, I explain the idea, but I don't ask you to implement these things. when you solve equations, sometimes we use lines, right? We use straight lines to solve equations, algebraic equations. But sometimes it may be better to use curves instead of lines. And the curve that we use is a parabola. Usually parabola can be written by second order function. By second order function we can write parabolas A, B, C, right? So by second order function we can describe a parabola, and then we can solve an equation by using a parabola. So instead of using these things, we may be able to use parabolas to determine solution position. So in the previous iteration, we used this kind of thing. We pick x0, and from x0 we use a straight line to find x1. And from x1 we use straight line to find x2. So this is the method developed by Newton, or iteration. Now we use different scheme. From x0 and a few more points, right? From some points. So x0, x1, and x2. We determine the third point x3 by using solution to this parabola, right? By using the approximation passing through these 3 points, and it will hit some point, right? And then we can find the solution, and then we determine this one. So this is the clear difference between the Newton's method and Miller's method. And as I mentioned, I'm describing it, but I don't ask you to implement these things, but idea is using parabola. Using parabola, we can find it. And because we are using second order function, the byproduct of this method is finding complex solution. This method can also track down the complex solutions because of this problem. So roughly this is it for the solution finding. And if you have any questions, ask me. If you don't, then I will cover the next thing, important thing that will be required in finite element method. Any questions about solution finding? So we want to find a solution by using various methods. But I only covered 3 important methods: bisection, Newton, and Miller's method. And I don't even ask you to implement Miller's case. Then the next case is this one. Integral. Why is integral important? I will explain the reason. When you want to solve differential equations, so I will use first order, ordinary differential equation. Assume that we want to solve a differential equation. Then we have only one equation, right? But in finite element method, we decompose these things using our basis function, say phi1 through phi200. Then for individual element, we need coefficients. That means we need a lot of equations. So how can you create a lot of equations from one equation? To do it, we create weak form, right? Initially, equation is given, but we create weak form, and weak form is doing what? Integral of these things with basis function, right? The basis function. Or then how many equations can you create? If we use weak form instead of given equation, how many equations can you create here? for individual phi sub I, we can create one equation. So total 200 equations can be created in the weak form. So this is the key. So please look at this. Once we have a differential equation, we have just one equation. But if we create weak form of the differential equation by using integration, then we can create a lot of equations, right? Then we can create system and then solve the system to determine coefficient appropriately. So this is the idea that we will cover. Then suddenly, to solve a differential equation, we need to do integration, right? We need to do integration. So this is the idea. So roughly, finite element method completely handles the problem by using finite elements like these. And for each element, we can create one equation. Then we have a lot of equations.
So each of the equations that is created is based on the other phi?
Based on each phi. Based on each phi. So for instance, initially we have this equation, right? And we create 200 different basis functions, and then for phi 1 we can have this. For phi 2 we can have this. Right? So now let's generalize this one. I want to handle this kind of case. Assume that you have this thing from alpha to beta or A to B. Then how can we integrate a function? And there are some methods, and roughly using area idea we solve the problem, and area idea gives us this kind of result. So generally f is given this way, and interval alpha to beta or A to B is given this way. Then the integral for the positive part, right, for the positive function, the integral represents the area, exact area. So this is the area, and this area is nothing but the integral, right? From calculus 1. Then how to find the area is our major concern, because area represents the integral. How can you find it? There are many different ways. First of all, assume that we use zeroth order function. Zeroth order function approximating f, or assume that we use first order function approximating f, or second order function approximating f. Then f can be approximated by flat function, right? Zeroth order function is a flat function. First order function is slant function. Second order function is a problem. So we approximate the f using either flat function, first order function, second order function. Depending on the choice, we have different formula. If we use this formula, then it is called the midpoint rule. If we use this formula, then trapezoid rule. If we use this formula, then Simpson's rule, right? So depending on our choice, we can create the thing. And it's not very difficult to find the area under the given function. So assume that for the interval, the middle point, right? So the middle point is chosen, right? Middle point is chosen. So this is the middle point of this interval. Then at the middle point, we can find the height, right? At the middle point, we can find height. And then we approximate the area by using this area. So you can see the difference or error between the area under the curve and the area that we approximate. So if you use flat function, it's called midpoint rule. Now this method is true off, so someone may say, oh, I want to use first order function approximating the points. Then first order function can be created, right? First order function can be created. Right? This is the first order function. then this is the area that we can calculate. Of course, you can see the clear difference, right? This is the clear difference, clear error. Or you can calculate the function using parabola, right? Using a parabola. Very, very close, right? This kind of parabola. So you can see the area under the function and under the parabola, and then you can see the differences. And then, so depending on these things, we can find different formula, and I provide a formula on my website, and these are the cases. So if you use midpoint rule, for the small interval, we can use this thing. Then we can accumulate these kind of things throughout the whole interval. So initially, take a look. If we have big interval, if we have a big interval, then we decompose the interval into small pieces, right? Into small pieces like this. And how can you calculate the area like this? We apply this thing. We apply this kind of thing, right? We pick something and then apply. And then we accumulate the area like this and then accumulate the area. What I don't want to see is this thing. Someone just use big chunk formula. I don't want to see this kind of big chunk formula. I always see, every semester I see this kind of big chunk formula. This is not the... But look at the error. Look at the error. But, so I don't want to look at this kind of thing. Always decompose and then apply these kind of things, right? These kind of things. So these are the things we can consider. And because we don't have time, I'll stop now. And next time you can ask about these things if you have questions, or email me questions. Here.
Just to show you, I totally misunderstood the last code question.
Oh, I see.
If you see, I erased it all.
Oh, I will read them.